Hello and welcome to Earthquake Tip number 8. My name is Dr. Shailesh Kumar Agarwal, Executive Director, BMTPC, and I'm going to present to you all about earthquakes, its concepts, terminologies, and how to construct buildings and structures to withstand earthquake forces through 32 earthquake tips, which are authored by Professor C.V.R. Murthy, mentored by Professor Sudhir Kumar Jain, and developed by IIT Kanpur in association with Building Materials and Technology Promotion Council, that is BMTPC. Through these tips, our aim is to spread right technical information in simple to understand language to our professionals who are in the field designing and constructing structures, especially architects and engineers. Before we start, let's make a pledge that any new structure we design or build must be earthquake resistant. The earthquake tip number 8 will elaborate on seismic design philosophy for buildings. The natural question comes to our mind that whether we should have earthquake proof building or earthquake resistant buildings. Let me first clarify this to all of you. As you can see in this table, the ground shaking can be minor, moderate, or strong. Minor shaking occurs frequently, moderate shaking occurs occasionally, and strong shaking occurs rarely. See in this table, about 800 earthquakes of magnitude 5 to 5.9 occur on an average annually, whereas only 18 of magnitude 7 to 7.9. So should we design and construct our buildings to resist that rare earthquake that may occur only once in 500 or even once in 2000 years, even though the life of the building itself may be 50 or 100 years? Since it costs money to provide additional earthquake safety in buildings, a conflict arises. Should we do away with the design of earthquake effects, or should we design the buildings to be earthquake proof, which means no damage during strong but rare earthquake shaking? The first approach to do away with the design of buildings for earthquake effects may lead to major disaster. And the second one, to have earthquake-proof building, may be too expensive. Hence, the design philosophy should lie somewhere in between these two extremes. Therefore, engineers do not attempt to make earthquake-proof buildings, but make buildings which are earthquake resistant. And as I told you, earthquake proof building means the building will not get damaged even during the rare but strong earthquake. Also, such buildings will be too robust and also too expensive. Instead, the buildings are made earthquake resistant. Such buildings resist the effect of ground shaking, although they may get damaged severely, but would not collapse during strong earthquake. Means we allow acceptable levels of damage, but safety of people and its contents are assured in earthquake resistant buildings. This is the major objective of seismic design codes throughout the world. So let's make earthquake resistant buildings, not earthquake proof buildings. Means let's allow certain degree of damage to occur in the building during earthquakes. Having said this, let me just explain you now seismic design philosophy, which is explained through this figure. As you can see here, under minor shaking, which may be frequent, the main structural members, that is, the load carrying members of building, should not be damaged. However, building parts that do not carry loads or non-load bearing members may sustain repairable damage. That means under minor shaking, the building will be fully operational within a short time and the repair cost will be small. Now let's move to moderate shaking. But this shaking may be occasional. The main structural members, mainly vertical members, may sustain repairable damage, while the other parts may be damaged to an extent that they may even have to be replaced after earthquake. That means after moderate shaking, the building will be operational once the repair and strengthening of damaged main members is completed. However, under strong but rare shaking, the main structural members, that is vertical members, may sustain severe, even irreparable damage, but the building should not collapse. There should not be any life-threatening collapse of building. That means after a strong earthquake, the building may not be functional for further use, but will stand so that people can be evacuated and property is recovered. In addition, let me also clarify here that consequences of damage of a particular building have to be kept in mind in the design philosophy. For example, important buildings such as lifeline buildings, hospitals, fire stations play a critical role during post-earthquake activities and must remain functional immediately after earthquake. Therefore, these structures should be designed for higher level of earthquake protection so that they sustain very little damage. Let me further give you the example of dams and nuclear power plants, which need to be designed for a still higher level of earthquake motion, as their failure may lead to secondary disasters such as flooding or chemical disasters. Let us see what damages in buildings are allowed during earthquakes. Earthquake resistant buildings, as explained earlier, means controlling the damage to acceptable level at reasonable cost. This philosophy is contrary to common thinking that any crack or damage in the building after earthquake means the building is unsafe for habitation. However, engineers designing earthquake resistant buildings do take cognizance of the fact that some damages in the building are unavoidable. Normally, different type of damages are visualized to cracks in concrete and masonry buildings during earthquake. Some of these cracks are acceptable in terms of both size and locations, and others are not. As you can see in this figure, in a RCC framed building with masonry infill walls between columns, the crack between vertical columns and masonry walls are acceptable, but a diagonal crack of such kind running through the column are not acceptable. You require services of qualified technical professionals to understand the severity of damage and their causes in earthquake resistant buildings. Let me give you another analogy for earthquake resistant design. We all know about electrical fuses in houses. To protect the entire electrical wiring and appliances in the house, we sacrifice small part of electrical circuit, that is fuses, during high electrical fluctuation. These fuses are easily replaced after the electrical overcurrent. Similarly, to save buildings from collapse, the earthquake resistant design is concerned about ensuring that damages in the building during earthquake are of acceptable variety, and also they occur at the right places in the right amount. These damages are like fuses, thereby saving the entire building. Now, to facilitate these acceptable damages in the building, the earthquake resistant design require ductility, which I will explain you now. To do this, let's first understand how different materials behave. Let's take white chalk. Remember, a chalk which is used to write blackboards, and steel pin with a solid head which is used to sheets of paper together. White chalk breaks easily. On the contrary, steel pin allows it to bend back and forth. This property that allows steel pins to bend back and forth by large amount is defined as ductility by engineers. So steel pins are ductile material, whereas chalk is a brittle material. Now let's look at earthquake resistant building. As you can see in this figure uh, uh, 4A, the main elements of building need to be built with ductility in them. As shown here, such buildings have the ability to sway back and forth during earthquake and withstand uh, earthquake effects with some damage, but do not collapse. The red line, as shown in this figure 4A, shows sudden collapse, that is brittle collapse, whereas this blue line shows ductile performance. This ductility is one of the most important parameters affecting the building performance, and therefore earthquake resistant design is priced to predetermine the locations where damages take place and then to provide good detailing at these places to ensure ductile behavior of the building. You can see in this figure 4b, which shows brittle failure of a column for the lack of good detailing, that is improper shear reinforcement or lateral ties. That's all about earthquake tip number 8. You can download this tip from www.bmtpc.org. The next earthquake tip, that is number 9, will be on how to make buildings ductile for good seismic performance. Thank you.